Hi, so in this video we're going to be looking at finding the volume of revolution. Now when we talk about the volume of revolution, we're talking about the volume created when a curve is rotated 360 degrees or 2 pi around the x or the y axis. There's two formula to learn for this. If the curve is rotated around the x-axis, we get the formula, the integral between a and b of pi y squared dx, and when it's around the y-axis, it's the integral between c and d pi x squared dy. And when it's the x-axis, you have the dx, and when it's the y-axis, you have the dy. Now this actually, although you don't really need to know this, it comes from summing lots of little cylinders along here between the A and the B, and the volume of each cylinder would be pi r squared dx, being the little cylinder's width, pi r squared dx, and the r actually, if you look here, would be the y coordinate. Anyway, so that's where it comes from, but you just need to learn these formulas. Okay, so here's an example. Find the volume formed by rotating the area enclosed by the curve y equals x squared, the x-axis, and the lines x equals 1 and x equals 2 through one revolution about the x-axis. So we're going around the x-axis, so we want the one with dx, so that's pi integral between 1 and 2 y squared dx. We substitute in for y, so that gives us y squared would be x to the 4. We're just then integrating a power of x, so you add 1 to the power, divide by the adjusted power, so that becomes x to the power 5 over 5, and then it's a definite integral, so you're going to integrate between these 2 points, so you substitute in the top point, and then you take away the substitution when you substitute in the bottom limit. So that gives you this, and then you put it in your calculator or work it out however you want, and that's going to give us 31/5 pi cubic units. There are often sort of funny answers on these, but don't worry about that. Okay, so find the volume of a solid formed by rotating the curve y equals sine x about the x-axis between x equals 0 and pi over 2. And I like this example because it allows us to revise our using trig identities to solve integrals. Okay, so again, we're rotating about the x-axis, so we want the dx, so that goes with the y squared, so we substitute our y squared in there, and then if you can remember, the double angle formula can be rearranged to give you sine squared x equals a half brackets 1 minus cos 2x in brackets. So I can substitute this in, and this is now something I can integrate. I can take that half out here, and the x gives me, when you integrate, sorry, 1 gives me x when you integrate, and cos 2x comes from sine 2x, and because it's 2x, so it's a constant times x, you divide by that constant. So that's something we've learned previously, and we need to put our limits back in between pi over 2 and 0. And so then we substitute in our limits. So when I substitute pi over 2 here, I get the pi over 2 from the x, but sine of 2 lots of pi over 2 is sine of pi, and sine of pi is 0, so I get nothing more from that. And then I substitute 0 in. X is 0, so that's 0, minus half sine of 0, and sine of 0 is 0, so I get nothing from that. So in the end, I get pi squared over 4 once I've multiplied this bracket out. Okay, I hope that's helpful. It's just a point of getting your formulae the right way round. If you just remember, when you're going around the x-axis, you use dx, and dx goes with y squared, and when you're going around the y-axis, you use dy and the x squared. Okay, I hope that's helpful.